Hey everyone, thanks for joining in. Today, my colleague Dr. Musa Taifi and I are going to talk about building low latency machine learning systems at adtech scale. So, what exactly is adtech and how is AI/ML related to it? So, Xandr is an adtech company and it provides a premium advertising experience to internet users across the digital, mobile, and CTV media globally. What does that mean? So, on the demand side, we enable advertisers to reach their target audience, show their ads, and achieve their advertising goals, that is, return on ad spend. On the supply side, we have publishers who are supplying high quality inventory where the users can view these advertisements. And most importantly, we have internet users who we want to provide a seamless, privacy compliant, premium online ad experience when they're browsing the internet in their browser or the apps. So, how does ad serving work? Let's look at the very right side where we have a user who is going to their browser and opening espn.com. Now, the browser sends an ad request to the ad server exchange. The ad server exchange is going to decorate this ad request with contextual data and audience information specific to this ad request. Then it sends the ad request to the bidding engine. The bidding engine is where the advertisers are sitting and who will want to participate in the ad auction. So the advertisers themselves go through phases of ranking where initially we narrow down candidates based on targeting and audience parameters. Later, we calculate the bid values based on their uh, bidding parameters, valuations, probability of click, conversions, etc. Finally, when we shortlisted a few advertisers who will participate in the ad auction, we pick the appropriate ad creatives that they might want to show to the user. So, an ad creative is actually the image or the video advertisement that you actually see on the internet. Now, all of these advertisers who've been selected at this point will send a dollar bid value back to the ad server. The ad server runs an auction, and you will see the advertisement on espn.com. And of course, at the bottom, the data store keeps track of everything that has happened throughout this transaction and maintains a historical data log. So, where does machine learning come in over here? As you can see, ML is used at like pretty much every stage of the process, right? Contextual and audience data uses deep learning, graph based modeling. Then in early stage ads ranking, again, you have like deep learning embeddings and similarity search algorithms. Final stage ad ranking uses classical machine learning algorithms, regression, again, some deep learning algos. Finding the right creative to show to the user, again, relies on reinforcement learning. And then there's more use cases like fraud detection, inventory quality models to make sure that we are not advertising on bad quality inventory and wasting advertiser money. There's applications like ad creative classification and categorization when advertisers upload new creatives. So ML and AI is used pretty much everywhere across the ad tech pipelines. So the big deal here is the ad tech system is not like a single process, but it's a distributed system of thousands of instances of bidding engines and ad servers, and they're running globally in various data centers serving their own local markets. Most of these ad auctions need to happen in under 150 milliseconds. Think about it, like when you open espn.com, the website opens almost instantaneously where you're able to see the content and the ads that are served. On a daily basis, Xandr sees around 600 billion ad requests. We conduct around 400 billion auctions daily, and about 10 billion, tens of billions of ad transactions are actually conducted. Auctions are won on the platform, right? So this is a serious business to serve ads to everyone globally, and we need to do it. And our AI ML is required at every step of the process. So, why is ML latency an issue? Because ML and AI is so prevalent over here across every stage of the pipeline, it's important that all of those algorithms that are running, they don't slow down our overall ad serving process. So when websites slowly, when ads are served slowly, it ruins the user experience and it may turn the users away from the app. Advertisers will be unable to reach their target audiences and fail to achieve their advertising goals. And publishers will lose significant revenue and more potentially viewership from users uh, if the site takes too long to load. So AI/ML is like really critical to deliver a premium experience to internet users. And having slow ML or like ML latency is a big problem because of that. Next, Dr. Taifi will talk about some of the common abstraction layers for ML serving latency.
So we have common abstractions layers. We can zoom out a little bit where we are, instead of being specifically for adtech, we can talk about common abstraction layers for ML serving latency and what to do about it. Next slide, please. So basically, whatever Chinmay was saying is that when you are building an ML application that's at this kind of scale, the first thing that customers will see and the clients will see is how long they're going to be waiting for the predictions. So that's what you want to focus on first. Next slide, please. So we have this little like roadmap for you to use. There's like a blog post also we wrote that describes this in more detail. But for newcomers that have never seen the sort of knobs and tuning parameters that can be applied to an ML system, this is a good starting point. We start from the left with an ML latency problem, and then we break down the various stages of where in your pipeline and in your serving layers you can optimize things. Next slide, please. So the first fork in the road is the ML latency you have online versus offline. The majority of the training and documentation and books are mostly about the offline world, either research or batch scoring of various ML applications. But in this case, what happens in the online side? Next slide. So on the online side, you find yourself in ad recommendations, ranking search results, predicting if a critical piece of equipment will fail, or how long is my ice cream gonna come to my home. And you can again fork your problem into asynchronous predictions versus synchronous prediction. In our case, for this talk, we're gonna focus on the synchronous predictions. Next. So the synchronous online predictions is where really the pain happens because of the current state of human knowledge around ML latency. Go ahead. So the way you want to think about it is you want to break the ML latency into two parts. There's the construction part of the prediction that you're going to get back from a service, and then you have the serving part of the prediction service. So the construction is where you reduce the time it takes a model to construct the prediction from a fully formed, well-behaving, enriched message prediction request. The prediction serving is everything else. It includes pre-computing, pre-processing, enriching the features, changing the input, and caching and optimizing the delivery of the output predictions. Next slide. On the construction side, that's what like traditional ML engineers are trained to do, is really optimizing the model itself, how we can impact the supporting components, and we can basically remove all the supporting components that are not necessary. And also on the core components, there's like a huge focus on hardware and compilation and optimization of the models. But the next slide, please. At its core, you're going to have a business problem that you're going to try to solve. And that business problem sets an upper bound on the ML latency that you can achieve. So a good way of thinking about it is you have two metrics that you're looking at. You're optimizing metrics that are the traditional ML metrics, map, MRR, accuracy. In the offline world, every new high or new low in these metrics is a win. people get excited about it. But on the client-facing side, there's a satisficing metrics which set a cap on, is the model going to fit on my device? Can the model run on a specific type of infrastructure that's given, that can't be changed? Is the feature processing going to finish within specific bound at request time? And does the model prediction satisfy the latency requirements? You really want to keep track of these two types. What next thing you want to do is, next PSA we have is that only so much can be done on the model itself. You, like, if you improve a model performance by 10% from a latency perspective, it will definitely get crushed by distributed I/O if you get out of core processing. Next slide. So on this map, now we are in the offline world, we are in the synchronous world, and we are talking about the serving. What can be done in the serving side? On the serving side, next slide, please. On the serving side, you have the real drag of the whole operation from our research is that the feature transformation and enrichment is the real drag, because you have a model input, and that model input might not be completely ingestible by the model. So you need feature lookups that are either static references or dynamic inputs. Next slide. So on the feature processing, you have user supplied features that come directly from the request, and then you have to transform them to something that the model understands, either through a static reference lookup table or a dynamic real-time feature that will come from other streams that you need to ingest in your model in real time. So increasing levels of complexity, really, like, you want to think about it in terms of your business problem. Not the most complex model might not be, even if it's the best in offline world, might not win in the business customer facing world. Next slide, please. So on the model outputs, you have two options for improving the latency. You can either pre-compute the predictions in a batch process. There you have two options again. Either you have an entity-based or a feature value combo that you're going to pre-compute the predictions for, and then you have caching, which you're just going to reuse predictions that you previously generated. There you either have an exact match for the predictions, or you need to use some sort of approximate matching for this cache. So if all the techniques covered so far still do not make your prediction latency low enough, then the next optimization, you need pre-computing and caching predictions, like I was saying. So the biggest problem you're going to have when you try to pre-compute is that you need to decide if it's going to be entity-based or a combination of feature values. If you're using an entity-based and you have a well-behaved entity, then entity ID, that's great. You're going to be able to just generate the prediction and look it up. But if you have a feature value combo, then you have to select which features are going to be included in the lookup keys. So here's an example of what can happen. Like, you have as soon as you add another feature type in your hash key, like country, county, device type, song category as the key, the multiplication of those are going to be will increase your lookup table and slow down your ML latency lookups during the feature. Both on the feature lookups and in the prediction lookups from previously cached predictions. Next slide. So what you want to do is that after deciding on the key, you pre-compute predictions on each key, and then you store each key value in a low latency database, and you're good to go. You know, even with a solid key value store, you still need to reduce the number of predictions stored by the reducing number of possible keys. So the guiding method of doing that is using this optimizing versus satisficing metric method here, where you set a cap on the network, on the ML latency, and then you try to reduce the number of the complexity of the lookup key until you hit a good optimizing metric, but you do not go over the satisficing metric. Next. So we are at the bottom here with the reusing predictions. Can you go next one? So you have this very special case of real-time similarity metrics where you are storing, you're caching the embeddings of the products, and then you build an index on them, and then from that index you use approximate nearest neighbor method. You load that in an ML prediction service, and then you use the index at prediction time to retrieve similar product IDs. Kind of examples of these libraries that you can use: Annoy and ScanNN. But what can I do if the index is too large? There's no magic bullet here. You have to reduce the embedding size to get a smaller index until optimizing metrics stops complaining. And until the optimizing metric starts complaining means that optimizing metrics now is not good enough for the business. And then obviously you have your cap on the ML latency budget. Next. So this is the DB will have a lot of rows, but only a few columns. So choose a DB that handles single key lookups very well for your prediction, and then you keep an eye on the categories cardinality. If you're generating those dynamically, keep strong monitoring on that. And then continuous values definitely need to be bucketized. And any technique that you can find to lower the cardinality of categories is your friend. So this is like, we have more detail in the blog post, but this is the map of options that you can use in your project. Now Chinmay is going to talk about a couple use cases.
So let's look at some of the real use cases that we face in adtech. So what we're going to do is we're going to go through the part where the bidding engine receives ad requests from the ad server and the process of generating matching ads with bid values, right? So when the ad server sends a request for bids to the bidding engine is going to go through its list of advertisers and try to rank them, shortlist them, and come up with a list that participates in the auction. The first part here is early stage ads ranking. So the goal here is to shortlist top ad candidates from a very large universe, let's say, hundreds of thousands of advertisers, to a few hundred ads that will participate in the next phase. So here, the model that we use is a two-tower deep learning neural network model that uses embeddings to match ads to the context of the ad request, right? So this model is trained on ads metadata and contextual features from historical ad data. And the hidden layers capture interaction between the features, which actually gives a much better performance than conventional models. The model itself is computationally expensive to build, which is why it's updated infrequently, about once every few days or so, on historical data. Right. So a very simple way this will work is when ad request comes in, we construct contextual feature embeddings from the ad request. Then we go and find matching ad embeddings using exact search that we built using the deep learning model before. Once we find similar embeddings, we go and look up the ads pertaining to those matching ad embeddings. And these ads are selected for the final stage of the ad ranking. So the good part here is that we have 100% recall because we did an exact search. The bad part here is both the model serving and the model construction latency costs are very high. Right? So we can do slightly better here if we use approximate nearest neighbor search. So approximate nearest neighbor, or ANN, relies on limiting the similarity search to a small local embedding neighborhood. Modern vector databases, which are used to store embeddings, have algorithms that allow you to index stored embeddings in such a way that you can do a quick ANN search and reduce the cost of the prediction construction cost significantly. And you still get a very high recall if you choose the right ANN algo for your use case. But the prediction serving costs are still very high at adtech scale. So we can do even better than the previous approach. We can combine ANN with caching. Because these models are computed once every few days, we don't need to actually construct extract features from add requests in real time and construct embeddings every single time. What we can do is we can pre-compute the add requests or like contextual embeddings and their lookups based on ANNs and store them in some sort of in a fast lookup database, right? This significantly reduces both of these approaches together significantly reduce the cost of uh, construction and serving the model. So our diagram looks a little bit like this. So when the bidding engine is performing uh, early stage ads ranking, what it's actually doing is it's doing a contextual to ads lookup in a fast cache, which is backed by everything else that's happening behind it, the ANN search and matching ads. But for most of 99% of the cases, all we're doing is a cache lookup, which is extremely fast. So the next phase is like the few hundred advertisements that we picked in the last phase come to final stage ads ranking. And the goal here is to further shortlist ads that will participate in the ad auction and calculate their bid price, right? So one of the models used here is a logistic regression model that's used to compute the probability of a click for a given request. Now, these models are trained fairly frequently using historical data because we want to have recent data contributing to the model, right? So the models themselves use like 15 plus features from an ad request to compute probability of a click or a conversion in real time. Just given the cardinality of our feature set, we are not able to pre-compute and cache all of these requests. Right. So here we can also implement the ML service API as a or this particular model using an ML service API that the bidding engines talk to. But here, the model serving costs would be significantly higher than the cost of prediction, which is just computing the logistic regression equation. So, an optimal design choice for us was to move model prediction construction closer to the actual calculation logic, which is inside the bidding engines, to minimize the serving costs. So now what we have is like our models are constructed outside of the bidding engine, but the actual model serving, that is construction and serving, both happen inside the bidding engine, closer to where the bid values are computed. Once we have picked the few advertisements that will participate in the auction, what we want to do is pick the best ad creative for a given ad request. So here's where reinforcement learning on historical transactions and how ad creatives have performed at a particular ad context in the past comes into the picture, right? So basically this step runs for a very small number of ads that have passed final stage ads ranking. Uh, Another consideration to make is advertisers also update their creatives and metadata very frequently. Creatives will vary by location, based on the language used there, based on other cultural cues. And this requires us to basically perform reinforcement learning or run these reinforcement learning models, train them more frequently than the two previous cases. Okay. So again, here, pre-computing and caching is very impractical because we are updating these models a lot more often. Advertisers really like to keep changing settings on these or updating the creatives at a very high clip. Moving reinforcement learning model serving into bidding engines is not ideal because ad creatives can be large and consume significant memory, and evaluating multiple reinforcement learning models on that are being continuously updated can get really expensive in time in terms of compute consumed inside the bidding engines. So an optimal solution here for us was to actually host this as a model serving API that the bidding engines talk to, right? Now, this works because our models can be creatives, metadata, and the reinforcement learning models can be updated as frequently as possible. We can scale like the part that's the model serving API as much as we need horizontally. At the same time, because the number of requests happening to add creative selection is much lower than the previous two phases, it is possible to incur the small cost of model serving by hosting it as a service. Right. So, in conclusion, uh, as my colleague mentioned, we want to focus on machine learning serving latency first because your client is going to notice it if it's bad, and you're going to lose business. Right. Optimizing the model itself will take you only so far. So you have to realize most of your latency comes from elsewhere, and you have to know how to uh, or you have to use other techniques to reduce it from distributed IO and model construction latencies. Right? You want to integrate your model in your production hot path early in the life cycle. This way, you can iterate upon the issues, the latency issues that you're seeing, and start tweaking them early on. You don't want to wait till the last moment to come up with the best model and realize that it just cannot deal with your latency requirements. And finally, this is something that like most data scientists and ML engineers discount a lot. They want their models to run in real time every single time, but that's not always optimum. Pre-calculating predictions and caching the results can be a very effective model serving technique. Thank you, everyone.